test that theory. So let's plot a new function. For example, let's plot 5x squared. If our observation is correct, the parabola of 5x squared should be closer to the y-axis than the 2x squared. So let's see what it looks like. And we were right, it got closer and closer to that y-axis. Let's see for when the a value is between 0 and 1. Let's do 1 over 32x squared. Now what do you think? If 1 over 32, we know it's less than 1 over 2, will this function be more compressed or less compressed than 1 over 2x squared? Will it be closer to our baseline, y equals x squared, or will it be further from our baseline? Well, let's take a look and see. Oh wow, so we almost have a fishbowl in here. It is further from our baseline. It got more and more compressed vertically. So for the same x values as the other ones, the y values are growing slower and slower and slower. That's why we call a function vertically compressed. So it looks like we've made the right observations. Now, in deconstructing that function, we've taken a look at y equals ax squared, and then we want to add a constant q. Now, what is the value of p when we just add the constant q? Well, if we look here, we don't have a bracket, which means that p equals 0. And we're going to take a look at three functions: y equals x squared, y equals x squared plus 1, and y equals x squared minus 1. And again, I'm going to use Geometry Sketchpad to graph the three functions. So the first one, we said it was our baseline, y equals x squared, so x squared. And we've gotten used to what it looks like. The next one that we're going to graph is going to be y equals x squared plus 1. And maybe for this one, we're going to draw it as a blue dashed medium line so we can tell them apart. And then we're going to graph, as we mentioned, y equals x squared minus 2. So it is x squared minus 2. And we said that one, I believe we had another choice of a dotted line. And we just have to make sure that we make it really thick so you can see it at home. So now let's look at the three functions. The first one is my baseline. It's the thin, continuous purple line. And that's my y equals x squared. Now, as soon as I added the q value of 1, of positive 1, my function has shifted up the y-axis by 1 unit. Now, its vertex has moved up. For y equals x squared, the vertex is at 0, 0. And we can identify that point. It is 0, 0. Right? The vertex is 0 and 0. Now, when we added the 1, the vertex moved up to 0 and 1. When I graphed y equals x squared minus 2, the vertex point moved to 0 and negative 2. It moved down 2 units. So let's see if we can generalize these observations and make some conclusions. Now, I do hope that you take the time to graph your own function in the graph space provided. So what can we say if the q value is positive? We can conclude that the function moves up q units, which means a positive number, and if the Q value is negative, the function moves down Q units or a negative number. See, so if the Q value is positive, the function moves up Q units. If the Q value is negative, the function moves down Q units. Let's test that theory by graphing a few more equations. Well, what if I wanna graph x squared plus, I don't know, 13? So x squared plus, or maybe 7, so we can still see it in the graph. Let's see where it moves. Look at that vertex where we can barely see that parabola. It's all the way up here. We can barely see that vertex point of 0 and 7. What if I want to graph y equals negative x squared minus 5? Again, since it's a negative a, the parabola opens down, and that vertex point has shifted down from 0, 0 to 0 and negative 5. So I really hope this visual representation helps you remember what is the role of Q for a parabola's graph. Now, the one letter that is left unanalyzed is P. Now, let's take a look at P. So again, in our chunking process of the vertex form of an equation, we looked at ax squared plus q, and now at a times x minus b squared. And in the interest of time, I have 3 graphs of 3 different functions with 3 different q values. Now, the generic form is x minus b squared. So in the first one, x squared, p is 0. In the second one, I'm taking a look to see what the p-value is for x minus 3 squared. And I want you to pay attention here because it's almost counterintuitive. My general form of a quadratic function in vertex form is x minus p. So, if my function has a negative sign inside of that bracket, p will always be a positive value. So think of it as the opposite value of that negative sign here. So in this case, it's p equals 3. Now, if the sign is positive, then p will be the opposite value, which means p equals to negative 5. So now let's take a look at our 3 functions. The purple line is my baseline. The dashed line is y equals x minus 3. Now, when p equals 3, my vertex moves to the right 3 units. And for the third one, when p was negative 5, the vertex moves to the left into the negative side of the x-axis 5 units. So what kind of observations will we be able to make? Well, if p is positive, the function moves p units to the right, and it means I have x minus a number inside the bracket. And if p is a number less than 0, the function's graph moves p units to the left on the graph, which means inside of that bracket I'm going to have x plus a number, x plus 5, x plus 2, x plus 3, and so on. What I do recommend you do at home is inside of this handout, after numerous examples provided for you, there is a generalization table, which I really want you to take a look at and complete at home on your own. Now, you do have an empty table with just the proper headings, and I want you to really think hard about how would you generalize each concept. I've given you the categories or the headings needed for generalizations, but you should go back and really think of the different categories for this generalization. And if you have any questions, I can provide them in class. I can answer or provide answers in class tomorrow. Thank you very much for this slightly longer lesson, and the next ones will be focusing more on practical applications of the graph of a quadratic function. And remember, the graph will always tell you a story. This kind of graph will always show you where that vertex moves, if it's up or down, if it's left or right, if it's stretched or compressed. The graph always tells us the story. So you shouldn't shy away for drawing even a very rough sketch of your parabola, because that will help you that much more in identifying the transformations, the translations of your quadratic function. Thank you.